balance is for a batch reactor, a semi-batch reactor, a CSTR, and an on-steady state CSTR are all essentially the same. So a couple important things about material balances when we're talking about reactors. Most important is we're going to do a balance on individual components. The next is our notation where Na corresponds to the number of moles, so total number of moles of A in the reactor. And Fa equals the flow rate of A. And again, this is moles, but for example, per second. And we're going to find it easiest to write a balance for each component and then solve the equation simultaneously. So for most realistic systems, we have multiple reactions, we have mass balances and energy balances because the temperature is changing. We can't solve the problems analytically, so we might as well just get in the habit of writing down the mass balances, and we should get in the habit of using variables, number of moles in the reactor, flow rate in the reactor, and in general, not the concentration, not the conversion as a variable. These don't work very well for lots of systems, and we'll see why as we move along. So the mass balance is the same form that you've seen before. The accumulation, this is in the reactor, and this means as a function of time. So this accumulation is due to the fact that we have flow in, and we have flow out, and we have reaction. So remember, we're making the balance on an individual component, so reaction can increase the number of moles, and the reactor can decrease the number of moles. So if we apply this mass balance to a simple tank reactor, and we're doing first a balance on component A, where, for example, we might be looking at a simple A goes to B type reaction. So the accumulation term is how the number of moles in the reactor changes as a function of time. The reason that's going to change is we have flow in, let's for now make that a constant value, flow out, this will change with time, and then we have a rate of reaction per volume times the volume of the reactor, contents that is. And then we're often going to find it easier to also write the mass balance for component B. General, B could be flowing in the reactor, B is leaving, and rate of reaction of B times volume. In order to solve this equation, we're going to need initial conditions, and the initial conditions are going to correspond to what is in the reactor at the starting time. So at T equals 0, the number of moles of A in the reactor, some constant, and the number of moles of B, also a constant. This now we can solve once we know the expression for the rate of reaction. And then this reduces to the other types of reactors. So let's look at those. So first let's mention so that this mass balance essentially corresponds to the startup of a CSTR. Generally, we want to run a CSTR at steady state. Often, however, well, always we have to somehow start it up, and this would be the balances determine what's the solution, because with CSTRs, the solutions depend on the starting point. So let's look at this mass balance also and how it applies for a batch reactor. So for a batch reactor, there's no flow in, there's no flow out, and that means our mass balance simplifies to this. A semi-batch reactor might be the case where, for example, we have flow in, or we're slowly adding one component to control reaction rate, but no flow out. So the balance for a semi-batch reactor might be something like that. And then balance for CSTR, and now we mean a CSTR operating at steady state. So derivatives with respect to t would be 0 if we're operating at steady state. And so the mass balance looks like this. It's independent of time, flow rate in minus flow rate out, rate reaction times volume. So an important aspect of all of these reactors, particularly when we have flow out, such as in a steady state CSTR, is the rate of reaction is evaluated at the exit conditions. What I mean by that is if we have, say, a first order reaction and the flow rate in, volumetric flow rate times the concentration. The flow rate out might be a different volumetric flow rate, though typically we're looking at liquids where it's going to be about the same, times the concentration leaving the reactor. So this is the exit concentration. But it's also the concentration in the reactor. So if we had a first order reaction, the rate of reaction would be the same concentration. So this concentration is the same as that concentration. If it's liquid phase, of course this is the most common condition that we have, a liquid phase tank. So liquid phase, if we substitute in to the mass balance, we'd have volumetric flow rate, concentration in, volumetric flow rate, concentration leaving, minus kCa times volume. So in general, of course, the temperature entering the reactor is not the same as the temperature leaving. This has to be evaluated at the exit temperature because the reactor temperature and the exit temperature are going to be the same. The reactor concentration, the exit concentration are going to be the same. So we can certainly simplify this more, but remember that typically we're going to have both a temperature, so an energy balance, a mass balance. We're going to have multiple components. Easiest to solve these numerically. So in order to understand how the temperature affects the reaction and what the temperature is going to be, that will depend on conversion. So we're going to have to write down also an energy balance and solve simultaneously the mass and energy balances. And the energy balance will be part of another video.